Hello and welcome to a new video. In this video we are going to talk about Maxwell's equations. If you study physics or engineering, you have seen these. They are Maxwell's equations. They are usually printed on t-shirts, mug, frightening exam papers, and if you are like most of people, you will look at them and see a wall of hieroglyphs. You will see symbols like as that, for instance, this integration, but not a normal integration, but this one, the circular integration, the nebula, the delta, and these strange magic sounds and shapes. What are these even? Why did they come out with these symbols? So you see these integrals, partial derivatives, and vectors. You are told to solve by x or for x, but that's the wrong way to look at them. These are just math problems. They are sentences, and this scary math equations morph into four simple English sentences floating in the air. So look at this equation, for instance. This is the first one. So before we get into this equation, we will talk about the scientist behind this, or the mathematician behind this. James Clerk Maxwell didn't actually write the four equations we use today. A guy named Oliver Heaviside, Heaviside, I can't really remember his actual pronunciation, but I'll name Heaviside for simplicity. They cleaned them up later to be on this form we can see now. It's a simpler form, but the one who formulated this smart things for smart equations from Faraday and Gauss and the great scientists and thinkers was Maxwell. So these ideas represent the most significant jump in human history. Before these four sentences, electricity and magnetism were two separate, nothing but a magical tricks. After these sentences, we had the blueprint for light itself. So today we are going to read the code of this let's call it universe. No calculus required, just simple concepts. Okay, so let's say for the first equation, for the as a prerequisite for the first equation, we have let's say a river flowing, and this river flowing is some parts of the water swirl sometimes, like the water is swirling. Sometimes you can find waves, these waves are swirls, or sometimes there's swirls within this water. Sometimes the water itself in the sink part, there's swirls. So these swirls, or they call it whirlpools. Other parts explode around from this underwater, like sometimes water get it like that, or does it get like that, or does it get like that, like with a clockwise direction? That if it gets, let's say if this is the center and points and arrows or forces extrude from this, we call this positive divergence. They call this divergence, okay? But this type is positive. What about if all these are getting, but this is divergence. Let's not talk about positive or negative, but there's one positive and one negative. If it's all joining onto this part, it's also divergence. But if this point has swirls around it, like the forces are extruding but on a form of a swirl, here it's not divergence, here it's called curl. So to visualize this as math, we usually draw divergence as nebula, or the delta dot whatever is gonna be written here. So this is the divergence, and if for the curl, we do the nebula cross this thing. Okay, so this is curl and this is divergence. Okay, so this was the first part. So now let's go with the point. Imagine that this universe, yeah, was filled in an invisible fluid, and this is the field, and the fluid is going, and we need two measurements on over this point. So we call this divergence, and this thing as this we call it sometimes sprinkler effect. If you look at the specific spot, the fluid appearing there is flowing outwards. That's positive divergence. If it's draining away, it's negative divergence. So this is negative divergence, and this is positive divergence. Okay, so this is positive divergence, getting in, giving energy to the thing, and this is negative, getting extruding outwards. Okay, so the other way was the curl, and this is called the swirl effect. If you dropped a twig in the water, would it spin? If yes, you have a curl. And that's it. Maxwell equations are just asking, does the electric field sprinkle like that, or does it is it a magnetic field swirl like that? Okay, simple as that. So now we're gonna talk about the first equation, and we're gonna observe what happens here. So this is called, firstly, this one is called Gauss law, okay, of electricity. Before this one explains the electricity. It was formulated by these symbols. So let's know firstly what these symbols are. This one is, we're gonna call it now nebula. This again, as we said, if it's nebula and dot, then it is divergence. It means that the electric field goes outside. Okay, so or whatever the field of this thing next to the nebula is going outside in a form of that shape, getting of a shape of not a swirl, but extruding from the point. Here we are talking that the nebula, or the divergence, since we said it's dot, divergence of E. E here we are gonna represent it for the E is the electric field. Okay, for the electric field, the nebula or the divergence is outside, it extrudes. Is it positive or negative here? So we see that the initial equation, it is positive here. So that means that if it's positive, it's supposed to be like that. The points are getting towards the point. For what? For the charge of the thing, or the charge inside a pipeline. So let's visualize this. So let's say that we have a cable here, and this cable, we want to know where the current flows here. The current, okay? So usually we know that the current is going on the opposite direction of the electrons. So this equation can be formulated sometimes on a different structure to be on a D, and here is a negative. Okay, here we know that the current in the electric field goes in opposite direction to the electric field. Yeah, the electrons is going on the opposite direction to the current. Yeah, so it says here that the electric field goes on a direction from a point outside to outside, if we were talking negative, to the charge, the amount of charge. This increases, or this arrow increases the amount of energy within it by the amount of charge in this line. Okay, so yeah, this epsilon naught here is just a number describing how thick empty space is. So that tells us how hard is it for the field to push through vacuum. So we are talking here like in vacuum. If there is a line, electric line going in vacuum, here it is like displayed or shown that the current goes on the opposite direction of the electric field by saying that it extrudes up an opposite direction to the electrons with a density of charge representing the cross section here. through epsilon naught, meaning that this system is in vacuum. Okay, so that was it for the first equation. It may not be that visible to us, but it can be understood from the next equation. The next equation is going to be simpler. So okay, so the second equation for the Gauss, this was Gauss law for electromagnetism. Okay, this was for electromagnetism. The next one is going to be for magnetism itself, for electricity. Yeah, for this was for electricity. So this was for electricity. This one is for magnetism. This one is a little bit more simple. So it goes as the following. So it is saying that divergence. Let's write it in a text form. Divergence of magnetism is an, let's say, an infinite loop. Yeah, so what does that mean? So when we said that the divergence when it was positive, it does like that. Yeah, it does get extruded. So this is divergence. When this is negative, so that it loses energy here. It's negative divergence. When it's positive, it gets energy. It gets the flow within it. Yeah, so this is positive divergence. What if the divergence is equal to 0? Here, the arrows gets outside from the point and gets back to it, and it gets out from it and gets back to it. So if we have seen a magnetic bar before, a magnet bar is usually well, let's say this is a magnet bar, but let's say here is the north, and here is the let's do that. There is the south, and here is north. So for north and south, let's do that with the same color. North and south. For this is north and this is south, we will find that the magnetism goes from north and gets back to south, and goes from north and gets back to south, north and gets back to south. The same idea here applies for the magnetism. So this equation has visualized for us how the magnetism goes through a bar of a magnet, or through the magnetism. So this one is called Gauss equation for magnetism. Okay, magnetism. Okay, magnetism. Okay, so for this equation for magnetism, let's explain this equation. So it says that nebula of B, so divergence of B, it's of B. This is for what? For magnetic. B here is the magnetic. B here is the magnetic field. Yeah. So for the magnetic field, the divergence is 0. Okay, so this is a general rule getting us to this visualization, telling us that the magnetism gets from a point and gets back to it, making an infinite loop. So this one was simple, yeah, but it's different from this one, that here it says that the electromagnetism gets from a point to the other point on a different direction of the current. Okay, so what about the relation between the magnetism and the electricity? Here comes these equations. So now we can see that there is now the magnetism and there is the electricity. Yeah, there's the electricity. So this one is called the Faraday's law. Faraday's law. Both were living on the same age, by the way. Like Faraday and Maxwell have worked on this equation. Faraday has explained to Maxwell, and Maxwell had formulated to and then Oliver has simplified the mathematics to be on this form that we see now and can understand in our days. So what does this mean? What does this have what what does this even mean? So again, this is not divergent, this is curl. Now how we know that this is a curl? This is now an Abela X or cross. This is curl. Now the curl swirls. And this is Faraday law. It tells us how to create electricity without a battery. Okay. This equation says that the curl or the swing of electric field changes the magnetic field that we see on a negative sign, represents the nature of resistance. I will represent this now. But okay, if we try to change this magnetic field, like shoving a magnet towards a wire, when did we see that? Something called Lenz's rule. Like, I don't know if you have seen this structure before, but like that. A coil, let's say this is a copper coil, and we have done this. This coil is coiled like that, and we tried to insert a magnet. Let's change the color. 1 second. Now we try to insert a magnet. Don't wanna do that. Okay, to try to insert a magnet. Let's say this is the magnet color. We try to insert a magnet here, north, and the magnet and go like that, south. Okay, so let's think if we try to insert this magnet here. Yeah, if we try to insert this magnet here, we will find that the electricity flows through the coil. Yeah, but by what? By the speed. It's not speed now, but it's not speed, but I will represent it by speed for now. By speed of getting this magnet within this coil. Yeah, so when we try to catch this magnet and get this magnet to enter it through this coil, we'll find resistance, and this resistance is visualized like that. This magnetism is visualized like that. When we try to insert this coil or this magnet within the coil, the electricity flows within, as in this form, getting throughout the coil, and tries to resist it on the other form. But what if this magnet was already inside our inside of our coil? So let's say if it was inside already of our coil, and we tried to extrude it, we tried to get it out of our coil, yeah, we will find that if we try to extrude that, the current will flow on the other side, like it will go on the negative direction of it. It was, and the last time it went like that. Now it will go like that on the other direction, and the current and the magnetic field will resist us getting outside, so it will give us a push with that in that form. That shape for us, that shape is like if we drew it on a different outside, we find that like this is, let's say here is the magnet, like it was here, like this here was the coil. The magnetism was showing like this, was all pointing to a point. This is the curl. Yeah, this is the curl, like the thing we drew, that it's curled here. See, it's not direct straight lines, it's getting on a curl on this form, and this is negative curl. Yeah, so looking here back, this is negative curl of electric field gets us here. It's negative here. Yeah, negative curl is by differential of B. So when it was static here, when the magnet was static here, there was no differential, so there was no curl here, there was no resistance of any sort, or getting electricity form or movement, or by any form or structure. But when we moved it outside or inside, there were resistance. This resistance came here, this resistance came here, so resistance came in the opposite direction of this magnetic field. So the magnetic field was coming like that, the electric field was getting outside, the magnetic field was getting outside, so the electric field was getting inside. Yeah, and it's by not just by magnetic field, it's by change of magnetic field. So if the change was high, if we got something of a high magnetic density and we extruded it fast, so there's a big change of magnetic density, so a big change of or a big curl of electric field will come out. That helps us with magnetism, that helps us with electromagnetics, it helps us with the things that generate electricity. If we know something that has high magnetism, we can generate electricity. Yeah, if we have something that we understood now, that if something has a big magnetism, something has a big magnetic field, it can get us even more electricity. And this opposite applies. If something has a high electricity, it can give us a great magnetic differential on the opposite side of the movement. Okay, and that's the explanation of this step or this equation. So change or the curl of electric field is negative, or the opposite side of the magnetic field, or the change of magnetic field. So the last one is Ampere or Maxwell. This is called Ampere-Maxwell law. Yeah, so it was Ampere-Maxwell law. Okay, this Ampere-Maxwell law, this is where Maxwell earned his place in history. Actually, this is like one of the strongest ones in especially in the theories of antennas, microwaves, and people usually who are interested with electrocommunications and communication theories. This is one of the strongest equations. So it doesn't really have too much visualization like the other ones, but we can say that. We can say it in a little story that like Ampere thought like magnetic fields were only created by electric current. So electric current, where we are calling I. Yeah, we usually say that V equal IR. Yeah, V equal IR. Yeah. So now we're gonna call I. We're gonna call the IJ. Okay, J is equal to the C over time. Yeah, the amount of coulombs per time. So, or it's the mass, or it's the mass of charge per unit area. So what we need now is that we're gonna call this. Let's consider the IJ. Yeah, let's consider this I of the electricity we know as J. So the electricity, which is J, or the electric current J, we know that it's flowing in a wire. It makes a magnet. But Maxwell looks at this math and realizes it was broken. It was violated by laws of conversation. Something was missing, so he added the term at the end as this. That's where Maxwell came in. This one, differential of a partial E by partial T. Okay, so what this equation actually says, a changing electric field creates a magnetic field. So if we read again equation 3, it says changing magnetic field makes electricity. Yeah, this one says change in magnetic field makes electricity. Yeah, this one change in electric field makes magnetism. This is equation 4. So do you see a loop here? Both of 3 and 4 are the same idea, but magnetism has added an extra part, this part. Yeah, so this is the moment physics changed forever. Imagine you wiggle an electron, that creates a changing electric field. Yeah, according to equation 4, this changing electric field creates magnetic field, but now that magnetic field is changing, so according to the equation 3, it creates an electric field. So like, yeah, they feed each other. An electric wave creates a magnetic wave. Yeah, an electric wave, if we can represent an electric waves, it creates another magnetic wave. Yeah, this electric wave creates a magnetic wave parallel to it, yeah, on the same time domain. So it creates this detached from the source while traveling in empty space, self-sustaining and forever. That's why antennas come in place. Like they extrude for us electromagnetic waves. And these electromagnetic waves comes with the speed of causality, speed of light in vacuum, if you are in vacuum, yeah. So Maxwell has calculated the speed of this chain reaction by two numbers in his lab, being epsilon E naught and mu E naught. The result came out to be exactly 299,792,458 meters per second. And by that, Maxwell looked at this paper and realized something. This is not just electricity, this is light. Maxwell has proved that electromagnetism and the things that propagate in electromagnetism goes by the speed of light, and he has perfectly calculated the speed of light to be the fastest thing, and we can communicate over these things to be over the speed of light. That's why we can communicate from different countries in millions of seconds. So imagine he looks at this paper and he just doesn't just explain magnets. He explains optics, radio, X-rays, and Wi-Fi. He unified the universe. So at the end, next time we see these terrifying symbols on a t-shirt, don't think it's just calculus. Think about the charges making field, magnetic lines and loops. Changing magnetic makes electricity, and changing electricity makes magnetism. That's it. Just visualization to these using mathematics. And now, thanks to this great scientists and mathematicians, we can see this video and enjoy and like and subscribe to this video because of these nice and great scientists. Thank you for watching this video, and I hope you liked it. Feel free to comment or ask me questions, and I hope you liked it, and thank you very much.